Hello, I would like to welcome you to this session on effective tools for design analysis and multi-objective optimization using the SDI Tools Apogee software. In this discussion, we'll be focusing on performing a design analysis using the sensitivity analysis and the Monte Carlo functions within Apogee. The SDI Tools software includes a suite of tools and utilities that support system engineering, design for Six Sigma, and product development. In this discussion, we'll be focusing on the Apogee tool set and the application of sensitivity analysis and Monte Carlo in the prediction of performance for a new design. The SDI tools will allow you to take in a new or an existing Excel worksheet, define particular cells as parameters as X parameters with variation properties, and define certain cells as Y responses for which analysis is desired to be performed. Within the SDI Tools Apogee software, you can perform various types of statistical analysis, including a statistical allocation, sensitivity analysis, Monte Carlo analysis, and you can extend this analysis to include optimization to constraints and goals for performing a statistical multi-objective optimization. In this discussion, we will look at the application of sensitivity analysis and Monte Carlo analysis. We will be examining a problem where an engineer has designed a second-order low-pass filter and has selected particular component parameters in terms of their nominal values and tolerances to be used in this design. The parameters that have been selected include those for the two resistors and the two capacitors in the design. Nominal values have been specified, and we've indicated that 5% tolerances will be used for each one of these components in terms of their uncertainty or variation about the nominal value. In this analysis, what we'd like to do is determine the probability that the following product specifications will be met. We have a characteristic on the response, or requirement on the response of this filter, that the cutoff frequency be at 1000 Hertz with the limits of plus or minus 10%, and then the frequency response shape Q will be at 0.707, also with a 10% tolerance. We know the equations that can be used to compute both of these responses as a function of the resistor and capacitor values used in this response. Now, in addition, we'll be specifying that each of these parameters, the resistors and capacitors, will have manufacturing uncertainties that can be represented with as a uniform distribution from the lower spec limit to the upper spec limit. So let's go look at our analysis that we're performing and see how we can determine our probability of compliance or non-compliance with respect to our responses and their given specifications. We have the design analysis set up in an standard Excel worksheet where we specified each of the component nominal values, and then by including equation cells in this worksheet we can calculate the nominal response for our shape Q requirement and our cutoff frequency FC requirement. Now, in addition, we indicated what it would be the percent tolerance for each one of these components, and then using the nominal value and the percent tolerance calculated what would be the minimum expected value for each one of the components, and then also the maximum expected value for each one of the components. And then we've also computed what would be the standard deviation of this uncertainty also, using the nominal value, the percent tolerance, and then dividing that tolerance half-width by the square root of 3 will give us the standard deviation for the uncertainty of each one of these parameters. So this information is calculated based on the nominal values that are provided, and we've also calculated then the nominal response based on these given parameters. So in this analysis, what we will do is go open the Apogee Tools, go to the Start menu, Programs. We'll go to the SDI Tools, open Apogee, and then we will have in the Add-ins menu in Microsoft Excel versions 2007 and 2010, you will have your toolbar for the Apogee functions. If you're using the prior versions of Excel, then the toolbar will be presented on your desktop for you to use. So in this case, let's go define our resistors as a parameter that will have some uncertainty about this nominal value. So we will click on the X icon for defining parameters. And what we're going to do in this case is actually go define each one of the conditions, the name and other parameters, using cell references using information provided in our worksheet. So let me click on this little button here at the end of this name field that will let us then go select a cell that contains the name for this particular parameter, in this case cell B4. Then we will go edit the distribution so that it's representative of this nominal value with a uniform distribution of plus or minus 5% at the limits. So we will go edit the distribution. I will go identify the distribution as being uniform, and then I will also select the minimum value as calculated in our worksheet and the maximum value as calculated in the worksheet. And then we can modify the distribution. We see we now have a uniform distribution from the min and max values for this particular component. Click OK. And we see now that this parameter will be defined with a mean of 18,000 and this uniform distribution, which happens to have also a standard deviation of 519.6. Now that we've defined this parameter, we see that it has a blue border around this cell indicating it's defined as a X parameter within the Apogee toolset. Now we can actually go set up the other parameters, R2, C1, and C2 in a similar fashion. But what I'd like to do is show you a shortcut you can use within the Apogee tool. Given that you've defined one parameter and use cell references for the name, the value itself, the min and max values, any conditions for this parameter, we can go use the copy function within the Apogee toolbar to copy all of these parameters, select the corresponding cells for the other components, click on the paste item icon that's in the toolbar, and now we have defined each one of these parameters using the appropriate cell references for the name, the min values, and the max values for this parameter. Now we can go define the responses that we want to perform the analysis on that will be a function of these parameters with the defined variations. So let's select the equation cell where we have the shape Q response calculated. We will click on the define response icon, and let's go ahead and define this one using cell references also. So I will select the cell with the name for this particular response, and then I can use cell references also for the lower specification, and I can also do the same thing for the upper specification. Now then I can do a similar activity of again defining this other response I have, or I can copy this setup, select the other cell, and then paste this setup for the other parameter. So now we've defined through this simple operation 4 parameters that have variation and 2 responses that we want to analyze with respect to that variation. So to confirm our setup, I can go to the formulation editor icon, and I can review the definitions I have for my parameters, in this case the x's in this equation. I can review the conditions that I've established for the response is y in this worksheet. So I've defined all the information I need to actually go perform either a sensitivity analysis or a Monte Carlo analysis. To perform a sensitivity analysis, we will go to the icon in the toolbar with we're taking the lower level variations and mapping those into the upper level variation for sensitivity analysis. So let me click on this, and it will ask us which responses we want to perform the analysis on. I can select either one of these individually, or hold down the shift key and do a left click and select all of the responses at the same time. Click OK. We get an indication that we're going to perform a sensitivity analysis frequency response shape Q against these 4 parameters. and that analysis will be performed. And then we'll get the dialog box telling us we'll have the sensitive analysis for cutoff frequency FC. Click OK to perform that analysis. So at this time, you can see in this workbook we now have our original worksheet for the filter equations, our sensitivity analysis for the shape Q, and our sensitivity analysis for the cutoff frequency FC. So examining the cutoff frequency FC performance results first, we see that we're provided with the equation value by plugging the nominal mean values into each of the respective equations, in this case for the cutoff frequency. We get the calculated response mean, the calculated response standard deviation, and those two conditions are represented in this plot showing where the mean value would be, and then assuming a normal distribution for the response, what that dispersion would appear to be against our upper and lower spec limits. And then the probability of non-compliance with respect to the lower spec limit and the upper spec limit are computed and then added together to give us a total probability of non-compliance. So in this case, for this particular response, we would see that we expect about 0.3% or 0.03, 3 out of 1,000 results to be non-compliant with our specification based on the variation properties presented in each one of these parameters. Other information that's provided is what the calculated first and second order partial derivatives are for this response with respect to each one of the individual parameters. We see what the variance contribution is for each of these individual parameters to the overall response uncertainty, and then the also computed mean shift contributions. So this particular response doesn't appear to be too bad and looks fairly acceptable in terms of its PNC. Now let's go examine the frequency response shape Q variation properties. In this case, we quickly see that we have more variation with respect to our spec limits and results that fall outside of our upper spec limit in this case. And in fact, the computed probability of non-compliance for this response is about 13.7%. So a higher PNC for this response than we'd have to the other. So we need to go back and do some adjustments between either the nominal values and or the tolerances for these components, and hopefully in order to get a more acceptable PNC for both of these responses at the same time. Now then, having set up this problem and performed a sensitivity analysis, the same setup can be used to perform a Monte Carlo analysis. So we can go to our options menu, we can select the Monte Carlo tab, and we can specify the number of trials that we want to perform in our Monte Carlo analysis, or given that we have a certain confidence interval that we want to support in our prediction of the probability of non-compliance result, we can actually also estimate the number of trials that would be required for a predicted PNC, assuming a maximum error for estimating that PNC. We can provide this information and then estimate the number of trials that would be required. So let's go with the 5,000 trials that I have specified here. And we will go to the Monte Carlo icon, the pair of dice that's in our toolbar, and click it to go perform a Monte Carlo analysis. So what we're doing in this analysis is selecting 5,000 values at random from each of the distributions for the 4 components, plugging those results into the response equations for Q and cutoff frequency, and then we will collect the results, and then we'll see those in an output report here momentarily. So here we've completed our 5,000 evaluations using selected values from the appropriate distributions. We'll go create a response workbook, and then we can also save all the parameter and response data if we desire to do so also. So now then, we're examining the results that we have from the Monte Carlo analysis. We can see the resulting histogram of all the computed results for the shape Q response. The red responses are those that are non-compliant with respect to our spec limit. In this case, the upper spec limit of 0.777 and a lower spec limit of 0.6363. We can see that out of the 5,000 trials, we had 726 results that were non-compliant with respect to the upper spec limit, which gives us a resulting P&C of about 14.5%. And we'd expect our 95% confidence interval to be in the order of about 13.5%, 0.135, and 0.155 for the upper spec limit. So this would define the upper and lower 95% confidence intervals about our nominal P&C result. Then we can examine the corresponding results for our cutoff frequency, and we can see the resulting histogram of results. And we see that out of the 5,000 trials, we had 5 trials that were non-compliant with the lower spec limit. None were non-compliant for the upper spec limit, and we have a resulting predicted P&C in this case of about 0.001, 0.1%, or 1 out of 1,000 would be non-compliant. And so these results were obtained from using the variation properties, selecting parameters at random from these distributions, plugging these into the response equations, and then collecting results to get a prediction of the uncertainty of the response. So through this setup, we have completed our sensitivity analysis and our Monte Carlo analysis. And so now we have determined the probability that the following product specifications will be met, or in our case will not be met, looking at the probability of non-compliance for both the cutoff frequency and the shape Q. So through this analysis, we've demonstrated that we can take an existing Excel worksheet. We can very easily assign properties to the X parameters, identify the Y parameters that we want to, or Y responses that we want to analyze, and then perform a sensitivity analysis and Monte Carlo analysis in order to assess the performance in the presence of variation. So in summary, by using the Apogee tool, we've analyzed the performance and predicted the quality of this design very early in the development process. We now have an understanding of the impact of parameter uncertainty on our specification compliance, and we basically simulated this design based on manufacturing conditions for these individual parameters, and we could have included other conditions related to operating conditions and other circumstances that may influence variation of the response. So basically, we've used this approach to support our product development, system engineering, and design for Six Sigma activities. We've analyzed this particular circuit design, which could be the end product that we're developing, or this could be a component that's included within a larger system that we'll be analyzing. And we see now that what we can do to improve the design and hopefully get to a better performing result to satisfy the needs of the stakeholders. So I'd like to thank you for attending this tutorial session on the use of the Apogee software for performing sensitivity analysis and Monte Carlo analysis. If you have questions or comments, please feel free to contact me via email or call me on the telephone, and I'll be glad to discuss your particular applications you may have for the SDI tools. Thank you.